Goedemorgen, good morning, and welcome to this state-of-the-art presentation. So, my colleague is Vivek Badami, and we thought about this presentation quite a bit because it's very difficult to do a state-of-the-art presentation to experts. There are many, many people here who do as well or better than we can at describing the state-of-the-art. So we decided to focus a little bit on perspective, give you a kind of a different view on the evolution of displacement interferometry and distance interferometry in this context of precision positioning. So we're going to do a little bit of history, a little bit of technology, and even some poetry at the end. So I hope you enjoy. All right, I'd like to start with a prologue. So like many of you, I arrived with my wife by train. We had a very good experience on the Dutch train. We were in Leiden over the weekend, and we went to Utrecht, and we came here, and everything worked perfectly. And I've since learned that the trains in the Netherlands are 100% powered by renewable energy, particularly wind. So that's kind of a nice thing. And I was able to take in Leiden a picture of one of the power plants that drive these trains. Yeah. Maybe explains why the trains are not always on time these days. So this gets us to thinking, well, okay, what is driving the evolution of the state-of-the-art in transportation? And I would argue that it's the wind. So what drives the state-of-the-art in interferometric precision positioning? Well, the traditional way of presenting this, and you can certainly do this, is to start with this slide. It's undeniable that ultra-precision manufacturing is heading towards smaller tolerances, so all of the metrology must get better. That's the traditional view, but our view is a little bit different. We think the progress in interferometry is also powered by the wind. So how are we going to convince you of this? So we've got some history, some discussion of what's driving precision positioning, a little detour in dispersion interferometry, which may be new to some of you. Then we'll talk about optical encoders and fiber-based systems, and then some final thoughts and philosophy. Let's start with some history. How did this all start? So we tend to start the story of precision positioning by kind of assuming that interferometry also started in precision positioning, but that's not really true. It was really about refractometry. In the mid-19th century, people were very interested in the speed of light. So determining the refractive index of the air was extremely important. So this is a German interferometer, but people say, well, okay, but what about Michelson? So here's Michelson with his beautiful young mustache. And he invented this design, which we think of as kind of the beginning of the precision positioning in interferometry. But this actually was not a precision positioning interferometer at all. It was a new form of refractometer. He was interested in measuring the index of refraction of the air. He was also interested in measuring the behavior of the medium, which at the time people thought must exist, the ether, to provide an inertial frame of reference to rationalize Maxwell's equations. So here is his famous experiment, also often shown as the beginning of precision positioning. But there's no precision positioning going on here. Everything is exactly anchored to a big piece of granite floating on Mercury. He's looking for what's happening with the ether wind in this experiment. So there wasn't any precision positioning going on there. Yet we know, because we've done this experiment, many of us, if you make a Michelson interferometer, you have an excellent way of detecting small motions. Every half wavelength you get a fringe going by. But this really wasn't used very much for this purpose because it was very difficult to count the fringes and get coherence and so forth. So there was a very limited use of a Michelson interferometer for the purpose of precision positioning before the laser. And of course, lasers changed everything. A German professor who's a mentor of mine, Johannes Schmiede, he said one time in a presentation that I gave, he said, oh yes, any idiot now can make an interferometer. He remembers when it was quite challenging to do so. So this did change everything, and what happened very quickly was displacement interferometry was born. Perkin-Elmer had a system that was a homodyne interferometer, and then we all know about Hewlett-Packard and the Zeeman split interferometer, and then Zygo got in the game in the 1980s with an acousto-optic modulated 20 megahertz heterodyne interferometer, and the acousto-optic modulator is that gold thing, looks like a little biscuit in the middle of this picture of the original Axion 220. What does a heterodyne interferometer system look like? For those of you who don't know, I have a little cartoon here. So you have a stage, you have this fancy two-wavelength or two-frequency interferometer. You have a retroreflector, and you shine light at that stage. And then to do the interferometry, you add the polarizing beam splitter, and that separates these two optical frequencies. When they're combined, you then get a continuous sinusoidal signal. And then it's up to the electrical engineer to figure out what the phase is. And you can do that with extraordinary precision. So this is a heterodyne interferometer system. It's really the backbone of most displacement measuring interferometers today. And they're very nice because, for example, you can do line of sight interferometry, which minimizes Abbe offsets very naturally. This is a modern system, so this I'll describe as the state of the art. These are some numbers that we are aware of for measuring displacement, angle, relative position, interferometrically on dozens of measurement axes. You can go to 5 meters per second state speeds, which is really fast. It means you have to take into account actually how long it takes for the information to go along the wire to the electronics. That's called the data age problem. The cyclic errors, phase cyclic errors have been driven down to well below a nanometer. The noise levels are extraordinarily low on these modern systems, 0.2 picometers per root hertz, and maximum data rates of about 10 megahertz, and a range of 20 meters. So this is currently the state of the art, but we're not done. There is a lot of progress going on. This is just one example. I was fortunate enough to be in Ilmenau for Interferometry Day earlier this year. So this is a picture of Eberhard Manske and this nano measuring machine, and that's Thomas Dresel from Zygo visiting there. So there's still a lot of work going on in precision positioning. And why? Well, there is, of course, this drive for greater precision, and a lot of it is being driven by the semiconductor industry. So there are these wonderful videos from ASML. Thank you very much, ASML. It's been great for presentations to have these. And it shows the inside of a semiconductor capital equipment machine for producing wafers. And these systems have at least 2 motions that have to be monitored extremely well: the reticle or the mask and the wafer. Those have to be very carefully coordinated and orchestrated in order to make wafers. So you've got things in motion that have to be measured, and you have to do them better and better as time goes by, because the only thing more powerful than a law of physics is a law of the marketplace. The marketplace will not allow you to say, I can't go there. So there has been this steady progression, and with each progression you have a problem that you need to have alignment at 1/5 of the feature spacing, and then the metrology allowance is usually 1/5 of that. So it's 1/25 of the feature spacing that you need for metrology. So that says that at 5 nanometer half pitch, you require metrology to 0.2 nanometers, which is really hard to do, especially if the stage is moving at 5 meters per second. Now, interferometers work best in vacuum, this we know. So we've had examples. We've had some talks on advanced LIGO. This is before you take the air out of the chamber. These guys are standing there. But when you actually make the measurement, you need to remove the air. This is another example. This is an ultra-precision A-sphere metrology system that we built some years ago for measuring the projection lens elements in a lithography tool. And this also works with all of the air removed. Why? Well, because air release spoils everything. So here's just a cartoon illustrating this point. As the air is flowing through there, of course, it's turbulent and is creating noise that is most of the time significantly greater than a nanometer. So why not just monitor the air with a wavelength tracker? Because these things do exist. And the answer, of course, is it's way too slow. It's not really measuring the turbulence, it's measuring the sort of average value of the air. And it's in the wrong place. You need to be able to measure right in the beamline. So in the 1990s, we had a quite interesting project to do just that. And it was called dispersion interferometry. Well, still is, called dispersion interferometry. So what is this? Well, the idea is to measure the air density right along the air path by the dispersion in the index, refractive index. So if you make a measurement at 2 different wavelengths, you will get 2 different results because the refractive index of the air is different. So now you have two things that you can use to leverage your lack of knowledge about what the contribution is of the air. So the difference provides the air density, air path, and then you can get high-speed correction for the air turbulence. So the system looks like this. You've got, for example, a blue and a red wavelength, and you're looking at the same time. You have two measurements, L1 and L2, and they're slightly different because of this index of refraction difference. That allows you to remove the air by first measuring at one wavelength, then at the next wavelength, and then you use some math, and what comes out is the physical length, and the index of the air has simply been removed. And this is, again, right along the beamline. So you're actually measuring where you need to be and as quickly as you need to measure. Now, it's not so easy to do this experiment. It was started many years ago for geophysical measurements for a completely different purpose, for earthquake detection. So over kilometers, you measure a distance, and you see if the mountains are moving back and forth, maybe more than they should. And so these geophysical measurements were done in the 1960s and 1970s, I think they still are, using dispersion interferometry methods. But now you want to take that idea and you want to go to sub-nanometer. To do that, you need to have, for example, this is the way we did it, we built our own frequency double helium neon laser, 633 and 315, with more than 4 milliwatts per channel, and then we built a variety of dual wavelength interferometers. Now, because of differential measurement, all of the tolerancing for cyclic errors and noise levels, these are all 10 to 100 times more demanding. So it's an extremely difficult experiment to do, but the prize is very, very high. So we worked on it, and we actually got some very impressive results, at least at the time, given the half pitches at the time. So here's an example. Here's a measurement at one wavelength. Here's a measurement at a different wavelength, and you can see they're dramatically different. They're slightly different, and the slight difference is entirely due to the refractive index of the air, and that allows you, with the math that I showed you, to come up with the corrected value. So this now is just the physical length. Again, right along the side of where you need to make the measurement. This was done in nitrogen, which was the popular atmosphere at the time, and the air turbulence was reduced from 8 nanometers to 1.3 nanometers. At that time, it was the most advanced and highest performance dispersion interferometry experiment that had ever been done. So what happened? Seems like this is a good product, right? No. The problem with this industry is you start a project at the 600 nanometer node, and when you're done, you're at the 180 nanometer node. So you go back in the lab and you make things better and you improve things, but the problem is it outruns your ability to make things better. And I mentioned you have to be 10 to 100 times better than ordinary interferometry to do this. So the requirements tightened by 4x during the project, and it simply outran our ability to improve the system, and the project was stopped. But the project drove significant advances in order to get to that 10 to 100 times. So new interferometer designs, new electronics, cyclic error correction, all of that stuff went into our standard products. So here again, I would say progress was driven by the wind. In the meantime, of course, the chip makers kept going and the airflow was improved to keep up with the demand, but eventually this was no longer sufficient, and what really did it was double patterning, because that really drove the metrology budget down to where you couldn't tolerate the air anymore. And that brings us to the next topic, which is heterodyne optical encoders. The whole industry switched over for the front end of the line. So optical encoders use a grating, and they have this nice feature that the air path is very short. So this solves your air turbulence problem while introducing a host of other challenges, like how do you make the gratings, how do you deal with the Abbe offsets, and so forth. But nonetheless, we want to do this, so let's do that instead. Even at the time, there were lots of encoders, lots of encoder options. There were even two-dimensional encoders back in 1991 that used gratings to move around for this purpose. But none of them at that time really had the performance. So there was a lot of work done around the world to make encoders much better. So photolithography requires a big leap forward. This is a big 2D grating that we're inspecting here for an application of this kind. So in addition to those gratings, you need a new encoder design, which is like a heterodyne interferometer. So here's a simple way to make an encoder out of a heterodyne displacement interferometer. It's exactly the same slide I showed before. All I'm going to do is put a grating in the way, and now you have a heterodyne encoder. The difficulty with this particular design is you're sensitive to both Z and Y, both lateral in-plane motions and out-of-plane motions. But if you add another channel, then you can separate those two. So this now is a heterodyne encoder. So these things are fun to make, and so we've made a lot of these things. This is a three-dimensional drawing. Here's a different design for the wafer stage. We have lots of Z motion, and in the design I showed you before, you have problems with beam shear. So in this case, the design is self-compensating for beam shear. You can have large motions at the wafer stage, and you still get good signal strength. So there's a lot of PowerPoint going on here, and a lot of these pictures actually made it into patents. So. Another aspect of the whole exercise, including coming up with encoder designs, is coming up with light sources. Encoders are inefficient, so you need a very high-powered laser. So here's a 20 milliwatt laser, and this takes us to the state of the art. So each one of these laser heads can drive 8 axes. The maximum velocity is now 8 meters per second. You can tolerate quite a bit of tilt. The Z range is plus or minus a millimeter. Very small cyclic errors, 50 picometer cyclic errors, using a variety of clever tricks. A lot of those patents have to do with that. Digital resolutions also in the picometers and data rates of 10 megahertz. So I have this picture that is from ASML from around that time, 2010. And it's a very nice illustration of the difference between free space interferometry and encoder technology, and also what you're trying to achieve. The picture on top there on the right, which is the terrible result, the awful result, is plus or minus a nanometer. That tells you how well the atmosphere is controlled inside these photolithography tools. But nonetheless, you need to be down much smaller than that. So it's a nice picture. So at this point, encoders are firmly entrenched at the front end of the line if you're not working in vacuum. If it's deep UV, then you don't necessarily require it. But this is what you do. Okay. The last technology I'd like to describe is a fiber-based absolute position sensor. So kind of a completely different positioning problem. And it relates to synchrotrons. So we had a couple of talks yesterday about synchrotrons. We thought we'd share a little bit of what we're doing on this topic. So there's a need for in situ mirror metrology for these things. These are deformable mirrors for focusing, and you need to change them in real time to keep the focus spot small enough to do your experiments. So you can do this by looking at that mirror with a variety of fiber sensors looking in different directions. I'm going to show you the geometry for doing that. I just wanted to briefly show you this picture. If you've ever done distributed fiber sensing for strain and so forth, you immediately recognize this as a coherence-based system where you can have one system box and dozens, maybe even over 100 different fiber sensors, all addressed using optical coherence. So if you've done that kind of thing before, this will make instant sense. If you haven't, I don't have time to explain, but there are a number of papers that we've written that do explain how this works. So this is the kind of sensor that you get, which now is completely passive, has no electronics in it. Passive fiber sensor. I just want to focus on a couple of the specifications. The number of channels, 64 with one source box, noise densities in 20 picometer per root hertz level, and absolute position repeatability of half a nanometer. So this is actually quite important for many applications where it's not just a displacement measurement over a very short period of time. Maybe you're measuring something on Thursday that you previously measured on Monday, and you need to get a repeatable result for the absolute position. And that's one of the things these fiber sensors excel at. So here's a geometry for that synchrotron mirror situation, where you've got the bimorph mirror and you have an array of these sensors. And the key thing is that these things can measure while the X-ray is running. So it's not a laboratory experiment. This is something that can operate while the X-ray machine is in full force. We have done experiments where we've measured the mirror in a lab using a Fizeau interferometer and have compared open loop mirror control with closed loop, and you can see the difference, and the difference is quite profound, and we hope will have a big impact on this particular technology problem. Okay, now synchrotrons work in the vacuum. There are applications in air. I'm going to share one that's speculative. We haven't done this yet, but we think this is quite a good solution. Here's the 30-meter telescope, which is kind of a ground-based competitor for the James Webb, which is stealing the attention these days. If you use adaptive optics, you can see through the atmosphere, even with a very large telescope, and get excellent results. But these segmented mirrors have to all be aligned with respect to each other. So you have this huge array of segmented mirrors, and they have to be positioned with piston and tilt correctly. So there's a geometry we've looked at using these little fiber sensors. It looks like a little Michelson interferometer. You can see it on the left. But the key thing here, in the context of what we're talking about today, is that each one of these sensors is operating in air, and small changes in temperature and small changes in pressure can introduce very large changes in the measured distance. So you need to know what's going on very close to where each one of those sensors is. And so for that, you have a special refractometer, a tiny refractometer. You can see there the size of a penny, which is shrinking every day, just like a euro. But these little sensors can now be distributed everywhere. These little sensors can also be made, if you're careful enough, with what amounts to a traceable artifact as a standard length. Because since you're measuring absolute length, you can measure the wavelength of light in air absolutely using one of these sensors. Okay, so that's a lot of technology that I hope you can see, in some senses, tied together by the air. So that leads us to some final thoughts. So let's take Does anybody recognize this guy? How many of you, and I'm sure there's some people here who know who this guy is. Yeah, so it's a Dutch audience. I can't show this slide in any other country, it doesn't work. But people here know who this guy is. This is Peter de Groot, a very famous Dutch singer. He was a kind of a counterculture hero in the 1960s, but he's still very active today. He keeps retiring and then he keeps coming back. Absolutely wonderful lyrics, very thoughtful songs that have contributed a lot to the culture, not just of the Netherlands, but I think of the Western world, frankly. Now, he has an interesting life. He was born in an internment camp during World War II in Indonesia. And his father's father was this man, Hendrikus de Groot. And Hendrikus de Groot is someone that I know. I have this picture because he is my father's father's father. So Peter and I are cousins once removed. I think that's the way it works out. So why is this relevant? Well, it's relevant because I would like to take a moment with this heritage, my family heritage, to recite a poem. So this poem was written by Vivek Badami, and it's called Ode to the Encoder. This blanket of air that gives us life causes the metrologist no end of strife. Turbulent air churns without poise, giving rise to measurement noise. Controlled it may be, but at the nanometer scale. For precision measurements, even a whisper is a gale. It's my favorite line. A way to weaken turbulent strength is to cut short the air pass length. This is achieved by a perfect mating of an interferometer and a side-mounted grating. The air with all its dithering cannot distract, for the metric is frozen in a material artifact. But what about Abbe offsets, you say? Multiple axes of measurement keep them at bay. And so if you ask, what is the state of the art? It is certain that encoders will play a large part. Thank you.